Hi. So now I'd like to talk to you about Kirchoff's rules, which are important for analysis of circuits. So Kirchoff was a German physicist. He lived from 1824 to 1887. He worked with Robert Bunsen. They invented the spectroscope and founded the science of spectroscopy, and they also discovered the elements cesium and rubidium. So in addition to all this useful work on circuits, Kirchoff did a lot of other great physics too. Now, what Kirchoff's rules are for is to analyze more complex circuits. So far, if you've watched my previous lectures, we've talked about finding the equivalent resistance and the equivalent capacitance for a series of resistors and capacitors and parallel connections. But if you have setups with, say, for example, more than one power source, then maybe you need something a little bit more in order to analyze the circuit and figure out what's going on with it. So with no further ado, let's talk about Kirchoff's rules. They're pretty simple. There's just two of them. So the first rule is called the Junction Rule, and all it says is that if you have a junction, which is just one or more wires splitting off into one or more other wires, where wires meet up, in other words, in a circuit, what happens is that the current into the junction has to equal the current out of the junction. So if you sum up all the currents that are going into a junction, those have to equal the sum of the currents that are leaving that junction. That's shown here graphically. You have a current I1 coming in from the left, and then that wire splits off into two parallel wires. And in those two parallel wires are currents I2 and I3. And so here, for this simple junction, the junction rule would be I1, which is the current into the junction, equals I2 plus I3, which is the current going out of the junction. This is a consequence of the conservation of charge. You can't create or destroy charge, and so if the charges are flowing along and they split off, then they have to go somewhere, okay? The next rule is Kirchoff's loop rule, and this says that if you sum up the changes in voltage in a complete loop, any complete loop around a circuit, then the sum of all those changes in voltage has to be equal to 0. So for example, you might gain some voltage from a battery and then lose some voltage as you go across the circuit component. Now this is just a statement of conservation of energy, because remember that the potential energy, say for example, for a charge moving through some potential difference is Q delta V. And so if you have a charge moving around a circuit, then the energy that the charge gains from one potential change, say moving through a battery, would then be dissipated or lost in the resistor. So this is just conservation of energy. Mathematically, what this will look like is you're going to sum up all your voltage changes, make the sum of those as you go around one complete loop. It's very important that it be a complete loop, a complete circle. You have to start and end at the same place, okay? If you go around the whole loop, then those sums must equal 0. Let me give you a little bit more information about this loop rule, okay, and help you avoid some common pitfalls. So let's say that you've got a resistor and you've labeled the current in the resistor as, say, flowing to the right, as I've shown here, okay? Now, what we're going to assume is that if you travel to the right, say going towards B from A, so that your final destination is B and your initial destination is A, right? Then energy is lost if you're going in the direction that the current flows. So the voltage will drop across that resistor, and the amount of the voltage drop will be negative IR, according to Ohm's law, okay? Now, let's say the current is still, you've labeled it as going to the right, okay? But now you're walking across the resistor the other way, so that your final destination is A and your initial destination, or initial place, was B, so that you're traveling to the left, even though you've labeled your current as going right. Well, in that case, you're going the reverse direction from the current across the resistor. The potential will be higher, okay, upstream than it will downstream. And so that would mean that you would gain voltage as you go across that resistor in the amount IR. Now, I'm going to encourage you, when you do your loop rules, not to do this. You'll just confuse yourself. What I like to do is draw the currents, label them all, and then go in the direction that I have labeled the current. And then I assume that any voltage drop that takes place across the resistor is minus IR, and I just don't think about it again. Okay? So if you do that, if you choose your loops and you draw your currents carefully and you always walk in the direction of the current, then you can always label the voltage change across the resistor as minus IR, and you don't have to think so hard about it. So that's what I encourage you to do. Otherwise, you might end up screwing up. Okay? That's my tip. Now, one thing that you might not be able to avoid is going the wrong way across a battery. That might happen if you draw your currents in the circuit a certain way. Then sometimes you might have to draw it so that you're going backwards across the battery. Okay, let me explain. We define the current flow as going away from the positive terminal of batteries, usually, right? So that if you only have, say, one circuit element and you've got a battery in a circuit, we've defined the direction of positive current as positive charge flow. Now that's not right, thanks Ben Franklin, but there you have it. Okay, so that means that when you walk across a battery here, all right, we're going from A to B here in situation C. Then what's happening is that as you go across the battery, you're going from the negative terminal to the positive terminal, and you gain voltage in an amount plus E. Okay? But let's say that you're still going from A to B, but now your battery faces the other way, where the positive terminal of the battery is on the left and the negative terminal is on the right. In that case, you're going across the battery the wrong way, and what happens is you're losing voltage. If you were to put your multi-mode probes at either side of that battery, then it would label a negative voltage, okay? And that's what happens. So if you must traverse a battery in the wrong direction, then you're going to lose the voltage according to the stated EMF of the battery. All right? Okay, an example is worth a billion words. Let's do an example for a multi-loop circuit shown here. Okay? The problem simply says find the currents through all the circuit elements for the circuit below. Okay? So here on the left there's an 8-volt battery. The positive terminal is facing up on the screen. There's a 5 ohm resistor and then a 20 ohm resistor in this middle wire of the circuit. On the bottom here, bottom right, there's a 10 ohm resistor. And then on the far right, there's a 15-volt battery that points upwards on the screen. Okay? So we're going to do this, apply our Kirchoff's loop rules. Now I have a certain set of steps that I like to recommend that all my students follow. If you get used to doing it a certain way, it's easier to avoid pitfalls. So here we go. My step 1 is always to draw and label all the currents. Okay? So now I have different currents here indicated in different colors. Alright, let me explain what I've got. I've got a current I, and it's in purple, and it flows downwards through that 20 ohm resistor. Okay? Now when it reaches the bottom here at this T, then part of it goes off to the left, and I call that current I2, and then I2 goes up the correct way through that 8-volt battery. Okay? And then it circles around through the 5 ohm resistor and then makes a sharp right and joins back up to go through the 20 ohm resistor again. So that's a complete loop. I starts there, goes down through the 20, and then you hang, turn up through the 8-volt battery, go through the 5 ohm resistor, and then back down again. So that's one loop. Okay? Now, I1, let's say that you're going down through the 20 ohm resistor, that's your current I, and then you turn and go through this 10 ohm resistor, and then upwards the right way through the 15-volt battery, and then back across. So the red is I1. I1 travels through the 10 ohm resistor and the 15-volt battery. Okay? I travels through the 20 ohm resistor downwards, and I2 travels through the 8-volt battery and through the 5 ohm resistor in the directions. Okay, labeled. So you can think of I1, I think of as going counterclockwise, right? And then I2 I think of as going clockwise. So that's how I've labeled it. Okay? Once you've drawn and labeled all of your currents, then you write your junction rule. If you've got more than a simple circuit like this one is here, you might have multiple junction rules. Okay? So here, what happens is the current flows down through the 20 ohm resistor I, and then it splits off as I've drawn it. And so it splits off. I2 goes to the left and I1 goes to the right. So my junction rule is I equals I1 plus I2. Okay? Now I usually try to name my main current I, and then I number what I think will be all of my smaller currents. That's what I like to do. You can do something different if you want. It's fine. Okay? So that was step 2, write my junction rules, right? Might be more than one. Next, I like to write my loop rules. Okay, so here we go. Now, it's easiest, like I said, if you travel in your loop in the direction that you drew your currents. Then you know automatically to subtract those voltage from your resistors and you don't even have to think about it. Okay? So here I've drawn 2 loops, alright? One goes through the 8-volt battery and one goes through the 15-volt battery. Now I'd like to add here that if I've drawn my currents incorrectly, that is, if I've put one of them going in the wrong direction, all that'll happen when I do my solution is that I get a negative number for that current. So if I were you, I wouldn't sweat it too much when I draw my currents. Just be consistent. Don't go the wrong way, okay, because you'll just confuse yourself, and stick with what you got. And then when you do your algebra and you crank through it, if you've gotten one wrong, if you've drawn it wrong, you'll just get a negative number, and it's no big deal, okay? All right, here we go. Loop rules. I'm going to start at my battery and go across the loop, okay? So if I start here at my battery, at my 8-volt battery, then I'm going to go in the direction that I've drawn for I2, which is clockwise, okay? I want to go clockwise. So if I go clockwise across my 8-volt battery, I'm going the right way across my battery and I gain 8 volts, okay? Now I'm going to assume I've drawn everything right, I'm going in the direction I've drawn my current, and so when I go across that 5 ohm resistor, I lose voltage, okay? So that means it's minus 5 ohms times I2, because I2 is the current through that 5 ohm resistor. Now continuing in my little loop, I'm going to drop down through that 20 ohm resistor. When I do that, I lose voltage, minus 20 ohms, and the current that's traveling through that 20 ohm resistor is I. Now to continue, I can complete back my loop, and I start where I end where I started, okay? So that's my loop rule. 8 volts minus 5 ohms times I2 minus 20 ohms times I is equal to 0. So that's my first loop. Next loop. I'm going to go through my 15-volt battery first, right? Going through it the right way, so that's 15 volts plus 15 volts. Now I'm going to turn and go down through that 20 ohm resistor. When I do that, the current through the 20 ohm resistor is I. So that's minus 20 ohms times I. And then I'm going to continue in my counterclockwise direction. I'm going to go through my 10 ohm resistor in the direction that I've labeled I1, and so my voltage drop will be minus 10 ohms times I1. And then I'm back where I started, okay? So my complete loop rule equation for the second loop is 15 volts minus 20 ohms times I minus 10 ohms times I1 equals 0. Okay? So I've got all my loops labeled. Alright, my loop rules are written. Now on to step 4, solving. It's important when you have to solve any kind of system of equations that you have the same number of equations as unknowns. Your equation will be your loop rule or rules, right? And your junction rule or rules. So you've got all of those. So I had one equation for my junction rule, that was I is equal to I1 plus I2, and then I had 2 loop rule equations, which I just listed. Now what I like to do is I like to use my loop rule equations and solve for what my numbered currents are in terms of my total current. Then I take those solutions and plug them back into my junction rule to solve for my total current. That's the process that I follow every time, and it works pretty well for me. If you don't like that, totally go with what you like to do, okay? But this is how I like to solve. So here they are. I'm going to take my loop rule and solve my loop rule equations. So I'll start with the one with the 8-volt battery. If I rearrange that equation algebraically and solve for my numbered current, which is I2, then I have 8 volts minus 20 times I divided by 5 ohms is equal to I2. Okay? Now, second equation was my 15-volt battery loop rule equation. If I solve that for I1, I get 15 volts minus 20 ohms times I divided by 10 ohms is equal to I1. Okay? If it takes you a second to follow the algebra, just pause the video, right? And then start me back up when you've got that. I'm going to move on to the next slide. My next step is going to be to take the forms that I have for I1 and I2 and plug them back into my junction rule. Okay? So reminding you what they are there, I2 is 8 volts minus 20 times I divided by 5, and I1 is 15 volts minus 20I divided by 10. Plugging that into my equation, I is equal to I1 plus I2, okay? Then I can solve. When I solve this, I end up with 8/5 amps minus 4 ohms times I plus 1.5 amps minus 2 ohms times I. Now there's a little bit of algebra in there. You can pause it if you don't have it. Moving on though, I then combine the terms with amps, ending up with 3.1 amps, and then combine the ones that are multiplying I, so I end up with the equation I is equal to 3.1 amps minus 6 ohms times I. Now I'm going to add that 6 ohms times I to both sides, and then on the left hand side I would end up with 7 ohms times I equals 3.1 amps. Then I would divide 3.1 amps by 7 ohms, and then I end up with my total current I is 0.44 amps. Now I'm going to take what I had for I and plug it back into my equations for I1 and I2 at the top of the slide. When I do that, plugging in 0.44 amps, for I2 I end up with minus 0.16 amps. And for I1 I end up with 0.62 amps. Okay? Now you can see I got a negative number. Alright? It's not a catastrophe. All it means is that I drew that current in the wrong direction. Okay? So, thinking about that, what does it really look like? Well, if you draw the currents now correctly in terms of the positive charge flow, right? Then what happens is I have this big 0.62 amp current that is delivered by that 15 volt battery. Then when it gets to this top junction right here, it splits off, okay? Part of it goes down through the 20 ohm resistor. I labeled that direction correctly, and that's 0.44 amps. But then part of it travels to the left through the 5 ohm resistor, opposite to the direction that I thought, right? That's the 0.16 amps part, and then it goes the wrong way through my 8 volt battery. There you go. Who would have thunk it? There it is. Alright, so like I said, if you draw it in incorrectly, then it's no big deal. You just end up with a negative number. Alright? I hope that helps, and if you have any questions, I'll see you in class.